Hey everyone, so hopefully you can hear me. So today we're doing a session on A-level physics and we're doing it on Newton's three laws. So that's a really nice session for us to be doing. It's really about some of the most fundamental bits of physics, or certainly of A-level physics. Okay, so I'll give us 1 or 2 minutes before we get going. But just in the meantime, I'll explain how this session is going to work for those of you who haven't been here before. So usually we split the session into two parts. So the first half an hour, we'll learn some stuff. Second half an hour, we'll learn some stuff. But in the middle, we'll do some exam questions. So after the first half, we'll do a couple of exam questions to check how we've understood the first half of the session, and then we'll move on to the second one. So hopefully that sounds good. Let's just check we're good. Yeah, okay, nice. Other things. So the chat is there. I might ask questions as I'm going along. If I think it would be useful to ask to see if people are able to answer, because it will help me to see if you're understanding. I think also if you have any questions about what I'm going through, if you're confused about anything, type it in the chat. And I'll keep an eye on the chat and I will try and answer any confusions or any questions you have along the way. Okay, so I think let's go ahead and get started. Like I said, if you have any questions, just pop them in the chat. Okay, so today's session is Newton's three laws. There we go, very nice. So let's begin. So just briefly, I'm Matt. I'm the lead physics teacher here at Snap Revise. I'm a physics PhD student, and I've been an A-level physics tutor for, yeah, I guess quite a while now, 7 years. Okay, so today we have three objectives. We're going to state and explain Newton's three laws. We're then going to calculate resultant forces and determine if a system is in translational equilibrium. And we're going to solve some problems involving weight and reaction forces. So this is all about calculating things with forces, all about equilibrium, which, as we'll see, is the special case where all the forces add to zero. Okay, so I think we're in a good position to get started. One thing that we'll do before starting either of the halves of the session is just review some things that we think could be important to have in the back of your head as we go through today's session. So some background knowledge, it would be useful to have. So there's not too much here really. It's just a little bit of stuff about how to reason with vectors and just a little bit about gravity. So let's start by talking about resolving and adding together vectors. So we'll begin by actually considering a pair of vectors that we want to add together. So if I have two vectors that are in the same line, although as you can see here, they could be in opposite directions. Let's say I have a vector that goes to the left and it has size 1. And let's say I have a vector that goes to the right and it has size 2. Remember that a vector is something that has a size and a direction. So we have the lengths of the arrows representing the size, the directions giving the direction of the vector. And because this arrow is twice the length of this one, it has, we say length 2, the other one has length 1. Okay, so when we have two vectors like this, we can add them together. And really, when we add vectors together, what we do is we add them tip to tail. So I could take, for instance, this, let's say this vector here. I take the tail of this vector, and what I do is I put it on top of the tip of the other vector. So I'm just going to redraw this vector 1, but I'm going to draw it starting here instead. Okay, very nice. Now, the entire arrow that goes from the beginning of these two vectors to the end of these two vectors, that's the result of adding them together. And in this case, since we went 2 steps to the right and then 1 step to the left, the result of adding these two vectors together is a vector which is just pointing 1 step to the right. Okay, so in this case, the resultant is another word for the addition of the vectors. The resultant of the vectors has size 2 minus 1 or just 1. Okay, so that's how you add vectors together. We didn't do the most confusing case in which vectors are pointing in different directions, but that's okay. We won't need that much today. But we will definitely be splitting up vectors that are at weird angles. So something we're going to need to understand how to do is to take a vector which is at some angle to the horizontal. Usually we like to split problems into the horizontal and vertical direction. So let's say the angle between the vector and the horizontal is this angle theta. And let's say this vector has size L or length L. Then we need to know that we can split up this vector into two parts. There's the horizontal part, which we then add, again, tip to tail to the vertical part to make the whole vector L. Now, the horizontal component of this vector is L cos theta. And the vertical component of this vector is then L sine theta. And if you added these two vectors back together, you get back the original one, L. So we know how to put vectors together and we know how to split them apart into pieces. The one other thing we're going to need to know is something that is not maths anymore. That was all just maths, but a little bit of physics to begin. We need to know what the acceleration due to gravity is. And the acceleration due to gravity is usually given the symbol g. And it has, for us in A-level physics, a specific value. Unless you're told to assume it's otherwise, you can assume that g is 9.81 meters per second squared. Those are the units of acceleration there. Now, something interesting about this, which we'll talk about more later, is that this value for the acceleration of an object due to gravity doesn't depend on the mass. So let's write this here, independent of mass. That means that as far as we're concerned, unless we start thinking about things like air resistance, the acceleration due to gravity, it doesn't depend on how much stuff is accelerating. So I can drop one brick or two bricks tied together to make a bigger brick, and their acceleration will be the same. It will still just be 9.1, no matter, even if it was 10, 20, 1,000 bricks. Okay, good. So that's the intro stuff it will be good to have in the back of our head for today's session. Now, let's go ahead and before we just start, I'm just going to go through the spec points that we're going through today. So if you're an AQA, these are the spec points. If you're on OCR, these are your spec points. And if you're on EdXL, then these are your spec points. Okay, really nice. So we're going to start by talking about Newton's first and second laws. And then the second half of the session will really be about Newton's third law. Okay, so let's begin by stating Newton's first law. We'll later see that, at least intuitively, Newton's second law kind of implies Newton's first law. But it's more informative to start with Newton's first law. So Newton's first law states that an object will stay at rest, or, so there's an or here, or move with a constant velocity. That's maybe the most surprising bit of this law, the constant velocity part. So stay at rest or move with constant velocity unless acted on by a force. Okay, so there's this special bit in here, the or move with a constant velocity, and we'll come back to that in a second. Let's first of all examine the part that people usually think about, which is an object will stay at rest unless acted on by a force. So let's take a look at this diagram on the left-hand side. Here we can definitely see a picture of an object at rest. In particular, I'm thinking about this book in this situation. So this book that is on the table. Now, in this case, it's not quite true that it's not acted on by a force. It is acted on by a force, but it's actually acted on by balanced forces that cancel each other out. So for instance, the book has a weight, which pulls it down. And as we'll talk about more properly later, there's another force on the book. The table is pushing the book upwards with what we'd usually call a reaction force. But these two things balance, like R plus minus W, because W is in the opposite direction, so we should give it a minus sign, is zero. So like the total force on this book is zero, and that's why it's going to stay at rest. So we should probably add in another word here, which you don't usually have to state, but it is actually important to have in the back of your head. Unless acted on by a total or resultant force. In other words, if the resultant force is zero, an object that is at rest will stay at rest. Now let's go back to the blue bit, or move with constant velocity. So let's imagine we had an object that was already moving at some velocity. Now, it's going to be easier to think about something in space for this. So let's imagine we have something like an asteroid, and this asteroid is moving with some velocity v. Okay. Now, our experience on Earth is that if we set something in motion, let's say we throw a rock in the air, then it will slow down and eventually it will stop. But the reason that it will slow down and eventually stop is actually because when we throw that object on the Earth, it experiences lots of resistive forces, lots of forces that try to change its velocity. For instance, when we throw the rock through the air, it feels air resistance, which tries to slow it down. Eventually, it's going to hit the ground and it's going to lose, it's going to experience forces like frictional forces, again, say as it rolls along the ground. Okay, so actually, if we imagine we're in somewhere like space where there are no resistive forces, where there is no force on the moving object at all, then it will just continue moving with the same old velocity. So this is this blue part. An object that is moving with some velocity will keep on moving at that velocity unless it is acted on by some other force. So I don't do GCSE videos here. So there are GCSE videos on the Stat Revise website, but these web classes I think are all just A-level. Okay. So this is Newton's first law, and it's super important, and it's slightly unintuitive. No worries at all. Okay, so let's do Newton's second law, and we'll see that actually Newton's second law kind of has something to say about Newton's first law. So Newton's second law says the following. The resultant force, so see the resultant force is coming up again, that's why they're related. The resultant force on an object is proportional to its acceleration, or in fact is equal to its acceleration multiplied by its mass. Okay, so that's a big wordy thing, but we can turn this into maths. Let's see what this says. The resultant force, that's going to be our F. Resultant force is equal to its acceleration, let's write that here, multiplied by its mass. There you go. Lots of words, looks confusing. Actually, if you write it as a formula, it looks nice and simple. And you may well just kind of already remember this under this law as F equals ma. So recall here, this m here represents the mass. It's typically measured in kilograms. The acceleration here, well, the a here represents the acceleration. I think I missed a C before when I spelled this. Acceleration. Yeah, there should be another C there. There you go. And the acceleration is in meters per second squared. Velocity is meters per second, and acceleration is rate of change of velocity with time. So you just divide by seconds again. So forces are typically measured in newtons, but looking at the other side of this equation, we can see that newtons are the same thing as kilograms meters per second squared. Okay, good. So let's continue. This is our second law. Maybe I should just mention a brief thing now, although we'll see this more properly later. So just because I mentioned this kind of connection to the other law, Let's imagine the resultant force was zero. That's what the first law talked about. If the resultant force is zero, the mass times the acceleration is zero. And if the mass times the acceleration is zero, assuming your mass is not zero, that means your acceleration is zero. And that's where Newton's first law comes in. If there's no force, your acceleration is zero, meaning whatever velocity you had, you'll just continue to have forever. Okay, we'll talk about that more later. So in the meantime, let's talk more about this resultant force and define it properly. So the resultant force is the total force. We've used both of these words already. The total force acting on the body. Let's have another go at calculating a resultant force because it's important we know how to do this. Acting on a body. Or the resultant of vector addition of the forces. So it's just two ways of phrasing the same thing. It's the total force, but the way you calculate the total force is by doing vector addition. Each force is a vector. You add them together by thinking of them as vectors and adding them as vectors. All the forces on the body. Okay, so let's take a look at this example at the bottom left here. We have some object with a mass of 5 kilograms, and we have two forces. We have a kind of left force of 10 newtons. We have a right force. Sorry, that's a right force. We have a force going to the left equal to 4 newtons. Okay, so the total force comes from vector addition, and we do this just like before. The total force here, let's take the right-hand direction as positive. Then we have 10, which is positive. We have 4 going in the opposite direction, so it becomes a -4. So we add these together, and we get a total force of 6 newtons. Now, we just introduced Newton's second law, which says F equals ma, which means the acceleration is equal to the force divided by the mass. So in this situation, we can now actually calculate the acceleration. The acceleration is the force over the mass. We just showed the force was 6 newtons. The mass is 5 kilograms. So altogether, that should be 1.2 meters per second squared. So if you know the force and you know the mass, using Newton's second law, you can calculate the acceleration. And that's great. If you know how hard something's being pushed and you know how much stuff it's made of, you can figure out how rapidly its velocity is going to change. And the way you figure it out is with quite a simple formula. So that's really powerful to know. Okay, so let's talk a bit about a special force called the weight. And we're actually now going to, in a sense, prove this statement I made earlier, that any object will fall at the same rate independently of its mass. So first of all, let's introduce weight. Weight is the force due to a mass being in a gravitational field. So weight is the downwards force. Downwards force. Acting on a body. Acting on a body. With mass due to gravity. With mass due to gravity. Good. So it has a formula. The weight can be calculated by taking the mass of our object and multiplying it by that number g that we introduced before, which was 9.81 meters per second squared. But let's imagine that we have some object m, and there's no air resistance. So the only force it's feeling is the force due to gravity, which is the weight. Then the resultant force, which we'll call F, is, well, it's a total force, and that's the only force here, which is the weight, and that's mg. On the other hand, Newton's second law says that the force is equal to mass times acceleration. Therefore, you can conclude that mass times acceleration is mass times this number g, from which you can conclude that the acceleration is equal to this number g. And notice here that we have now derived this formula for the acceleration, and we've figured out that it's always going to be 9.81 meters per second squared. And we've figured that out independently of the mass. In fact, if you look at this calculation, you can really see why the mass didn't matter. In the step before, in this calculation, we had the mass on both sides, and I just cancelled those masses out. I divided both sides by the mass, if you like. Okay, so this is the source of what will often be referred to as something like Galileo's experiment, in which I'm not sure if it actually happened or if it was a thought experiment. But the idea was Galileo at least imagined dropping a pair of balls of different mass off the Tower of Pisa and wondering which of the balls would hit the ground first, even if, say, one was heavier than the other. One may be a bowling ball, the other may be made of paper. Now, because of air resistance on Earth, they would actually hit the ground at different times, which is why it was hard to have had this thought to begin with. However, if there were no air resistance and the only force actually acting was the force due to gravity, then the paper ball and the bowling ball would hit the ground at the same time. Good. Okay. And that, I think, is, at least when you first hear about it, somewhat counterintuitive. Essentially, because we live in a world where we do have to deal with things like air resistance all the time. Or drag forces, anyway. Okay, so now we're going to introduce a central concept that's going to come up a lot in A-level physics, really important concept. And it's just a particular situation an object can be in, or we'll say a body can be in. And it's a situation where the total force is zero. So we talked about this a bit already. It's the situation in which Newton's first law applies, in fact. So we call this situation translational equilibrium. So we'll say a body is in translational equilibrium if the resultant force, that's the total force, remember, the resultant force acting on the body is, drumroll, zero. Now remember, resultant was a fancy word for total. So a body is in translational equilibrium if the total force on it is zero. Okay, now let's remember Newton's second law. Newton's second law said F equals ma, but if F is equal to, if the total force is zero, in other words, if we're in equilibrium, then that then tells us that the mass times acceleration must also be equal to zero. So let's write that here. In equilibrium, the mass times acceleration is zero. And as I was saying before, assuming your object has a mass, which I think any object you can imagine does have, the only exception is maybe something like a photon, which you'll see about more in particle physics. So any reasonable object you can imagine, it has a non-zero mass, and therefore if mass times acceleration is zero, it must be because the acceleration is equal to zero. So that's a big thing. Equilibrium. If the examiner ever tells you that a body is in equilibrium, even if it's moving, that's okay. It means the acceleration is equal to zero. So this word means a concrete mathematical statement whenever you see it. Okay, good. That's very important. And notice if the acceleration is zero, that means the velocity is constant. Why is that? Well, acceleration is the rate of change of velocity. If the rate of change of velocity is zero, that means the velocity is not changing with time. That means it's constant. This is Newton's first law. Newton's first law. Newton's first law says that when the total force is zero, in other words, when we're in equilibrium, what that means is the acceleration is zero. So Newton's first law is this arrow in a way. Equilibrium tells us acceleration is zero. Okay, let's look at an example. Let's imagine that we're told that this object that we're looking at is in translational equilibrium. Often they will not worry about saying translational, by the way. Equilibrium. Often you'll just be told the object is in equilibrium. Okay. Then in this situation, let's try and compute what this number t must be and what this number theta must be. So what actually is this diagram we're looking at here? We're looking at a free body diagram, a diagram that shows all the forces acting on an object. Although we're going to imagine that this object is above the surface of the Earth and so is also feeling a force due to its weight. And remember, its weight is its mass times g. and its mass here is 7. So there's a force of 7g pointing downwards as well. So in this situation, if we're told the object is in equilibrium, we're told some maths. We're told exactly that the total force is 0. Remember, equilibrium means this. It means the total force is 0. Okay, and we can use this to figure out t and to figure out theta. So the trick here is that we can conclude from equilibrium that the force is 0 in any direction. So we're going to start by thinking about the horizontal direction. And in this case, the weight doesn't matter. The weight isn't in the horizontal direction, it's in the vertical direction. Similarly, the only bit of this T force that matters is the bit that points in the horizontal direction. So this is where we have to split our vector into two pieces. So here, what do we have in the horizontal direction? To the right-hand side, we have T times cos of theta. That's the horizontal bit. And we know that since the total force is 0, that balances the force to the left-hand side, which is this 14 newtons. Let's call this equation 1. Now we're going to think about the vertical direction. In the vertical direction, we have T sine theta here. And this must be balancing the weight that pulls things down, and the weight is 7g. So that's equation 2. Now, if you haven't done a problem like this before, where you're doing Newton's law and you're having to deal with two directions, you might not be familiar with the pair of mathematical tricks that we're going to make use of. But if you're aware of these tricks, then you will, well, just the trick, I guess, that we're going to use, it will help you a lot. So I wouldn't expect you to come up with this at all, but once you've seen it, hopefully you can recall it. So the good thing to remember is that tan theta is equal to sine theta over cos theta. So that allows us to take an expression that looks complicated because it's got like two trig functions in and make it something simple, something that's got one trig function in, this tan theta. So then a classic trick in these situations is to take one equation and divide it by the other. So let's look at the left-hand side. On the left-hand side, we have t cos theta divided by t sine theta. Now, I guess I actually wanted to go the other way around. I wanted to do sine theta over cos theta here, so that I could use this trick I just introduced about tan theta. Yeah, okay, so recall that tan theta is equal to sine theta over cos theta. But I can just put a t on top and a t on bottom. T sine theta over t cos theta. But equation 1 tells us, let's see, I don't think I did actually get 5.28. Let's see. So I'll show you what number I got in a second. So this is t sine theta over t cos theta. T sine theta was 7g. T cos theta was 14. We can check that in a calculator. And in fact, we don't need to. We know that from this, tan theta equals 7g over 14. Therefore, theta equals the inverse tan, which you can put in the calculator, of 7g over 14. And this is a number you can find out from this, that the angle here, theta, is 78.47 degrees. Okay, great. Now, since we know this, we've already figured out theta, that's great. We can now go back to, say, equation 1 and use it to figure out t. So we know that t cos theta, this is equation 1, is 14. But now that tells us t is equal to 14 over cos theta. And we know theta now. Theta is this explicit number here, 78.47 degrees. So we can check that in a calculator. And if we do that, we'll get 70.08. And that's 70.08 newtons. Okay, good. Hopefully that's making sense. Hopefully you now understand how to use the fact that an object is in equilibrium to calculate various sizes and angles in your free body diagrams. So how's everyone feeling? Does that make sense? And does anyone have any questions? 1, nice. Okay, so let's go ahead and do some exam questions. If you do have any questions about what I've been going through, just let me know in the chat. Okay, so this first exam question begins with a definition. It asks us to define the Newton. This is really nice because we didn't do this explicitly. It's a good thing to have practice with. If you're asked to define a unit, the usual trick is to think of the formula where the quantity that unit describes appears, the one that defines it. Yeah, I believe it will stay on the channel forever. I think I flipped through the other day and I saw that all the previous ones are on the channel. So it should still be on the channel, yeah. Okay, so what equation defines the force? Well, the key equation that force appears in is F equals ma. Once we've identified this, and we know that this is the thing that's measured in newtons, we can figure out how to say how to define a newton. And the idea is 1 newton, well, that will mean this left-hand side of the equation is 1. And that will happen when everything on the right-hand side is 1. This is the usual way to think about it. So once you know this, you can say 1 newton is the force. And let's read the other side of this equation. The force, which gives, what have we got? 1 kilogram here, and this is 1 meter per second squared, which gives 1 kilogram and acceleration of 1 meter per second squared. Good, so that's the usual trick. Find the defining equation and say 1 lot of your unit is what you get when everything else in that equation is also 1. That's the only trick I really used there. Okay, part B, which is going to be more about doing calculations. Figure 3.1 shows a spaceship on the surface of the Earth. The mass of the spaceship is 1.9 times 10 to the 6 kilograms. During liftoff, the spaceship rockets produce a vertical upwards force of 3.1 times 10 to the 7 newtons. Let's draw this in the diagram. So we have 3.1 upwards, the vertical upwards force, 3.1 times 10 to the 7. And they mentioned the mass of this thing is 1.9 times 10 to the 6. So that tells us this thing has a weight that's coming off the Earth, and its weight is mg, and that's going to be its mass times 9.81. Okay, so we've interpreted the question and labeled the diagram. We may have to redraw the diagram on this page, but that's okay. So let's see what we're asked. We're asked to calculate the weight of the spaceship. We'll recall this spaceship, which I'm just going to draw as a blob of mass now. There was this upwards force that has nothing to do with what we're looking at here. What was that? 3.1 times 10 to the 7. And down here we have the mass times the gravitational acceleration, and that's the weight. So the weight is equal to mg. And we were told already that the mass was 1.9 times 10 to the 6 kilograms. And g is always 9.81. So if you chuck that into a calculator, you'll get 1.863 1 times 10 to the 7. But that's way too many decimal places for what we need here. If you notice, what we were given was the 2 significant figures. So let's round our answer to 2 significant figures, at which point we'll have 1.9 times 10 to the power 7 newtons. There you go. Next question, calculate the initial vertical acceleration as the spaceship lifts off. Okay, so we have this object. It has 2 forces on it. It has the weight, which is 1.863 times 10 to the 7. That goes down. And we have this upwards force, 3.1 times 10 to the 7. Remember, we have F equals ma, which will relate these forces to the acceleration. But recall what the F has to be. The F has to be the total force. So the acceleration is the force over the mass, but this force should be the total one. Well, the upwards force is bigger, so let's do the upwards force, 3.1 times 10 to the 7, minus the downwards force, 1.8631 times 10 to the 7. It's good that the upwards force is bigger than the downwards force, otherwise the rocket wouldn't take off. And the mass was 1.9 times 10 to the 6. So we chuck that into a calculator and we'll get 6.5057. And that's it. Nothing else here. Meters per second squared. Again, everything was given to two significant figures. So that's way too many significant figures. 6.5 is perfectly good. Good. Hopefully that is making sense. We're now ready for the... Oh, no, we're not doing the second half of the question yet. We have another question. And this is a good one, partly because it will force us to acknowledge something about exam questions. Okay. Figure 4.1 here shows a method used to knock down walls. Okay, so we have a crane, we have a wall, we have this object, and the object has been given a three-body diagram. M is a heavy steel ball suspended by a cable in which the tension is T. T is drawn on there. The ball is pulled to one side by a horizontal force F until the cable is at 30 degrees to the vertical. It is then released so that it swings into the wall. The weight of the ball is 2,000 newtons. All of that information is in the diagram. We are asked now to determine the force F using a triangle of forces or a scale diagram of the forces or by resolving forces. Okay, so I expect that somewhere else in this exam question, an extra piece of information will have been given. If we hadn't been given this information, we wouldn't be able to answer this question. So we're going to have to assume that this object is in equilibrium. So what does being in equilibrium mean? Being in equilibrium means that the total force is zero. Total force is zero. It makes sense to not bother writing it here because I think it's clear that the idea is this ball is kind of held there and then they let go maybe and then it hits the wall. But it's something we're going to have to assume. Otherwise, we just wouldn't have enough information to answer this question. Okay, so once we assume that the total or resultant force is zero, then we can answer the question. And just like before, we split the situation into the vertical part and the horizontal part. In fact, we'll do the vertical part first. So in the vertical direction, what are our forces? Well, we have the force downwards, which is 2,000 newtons. And that must be balanced by the upwards force, which in this situation is, well, here we have a T and the adjacent here, this part here, which is the bit we need. That's going to be T cos 30. This part here is going to be T sine 30. Okay, good. So 2,000 equals T cos 30. So that implies we can find out T. T is going to be 2,000 divided by cos 30. Chuck that in a calculator and you get 2309.4. And that's newtons. Now let's look at the horizontal bar because we want to figure out F. So F is this force here. So we're just going to balance forces again. This time, the force to the right-hand side is F, the thing we want to calculate. And the force to the left-hand side is T sine 30. Okay, that's great. That means the force is equal to 2309 because we just calculated T. It's 2309.4 times sine 30. Remember, that's degrees. You can chuck all that in the calculator. And if you chuck all that in a calculator, you'll find that F is equal to 1154.7 newtons. In other words, the total force here is the two significant figures again, 1,200 newtons. Okay, good. Hopefully that's all making sense. Okay, so now we are ready for the second half of the session. And the second half of the session is about the third and final law. So what was the third and final law? The third and final law was Newton's third law, and it tells us that every action has an equal and opposite reaction. Okay, action and reaction are quite abstract words. You can really think of action as just being force, but we'll write it in the standard way first, then we'll explain it. So the way it's usually stated is Newton's third law says for every action, there is an equal and opposite reaction force. So let's say action force. There is an equal and opposite reaction force. Okay, this is actually quite a beautiful law. Secretly, this law is actually what gives you the conservation of momentum law, but we won't be proving that here. But what it tells us is that forces come in pairs. So if something is pulling something to the left, the other thing is pulling the first thing to the right, and so on. So as in classic examples, maybe the most familiar one would be something like if you press your hand into a wall, then you're exerting a force on the wall. There's no doubt about that. However, you feel it, and you're not the wall. So why are you feeling the force? Well, what you're actually feeling is the wall pushing back on your hand just as hard. Maybe to emphasize it's just as hard, let's make this out. Another example is an object in the Earth's gravitational field. For instance, the moon. Okay, the Earth exerts a gravitational force on the moon. That's why the moon doesn't escape and it orbits around us. So it feels a force due to gravity. And that's the way we usually think about things. But if you've ever heard about the reason for the tides, you'll know that the moon also exerts a gravitational force on the Earth. And that force is maybe more surprisingly equal and opposite. It just has less of an effect on the Earth, this equal force, because the Earth is so big, it has a big mass. And therefore, the acceleration caused by this force is very small. Okay, so that's one concept. When we're dealing with more kind of standard day-to-day objects, more like the situation in the left than the situation on the right, we often come across things that we'll describe as normal contact forces. So let's explain what that is. A normal contact force is a specific reaction force. It's just one situation in which there's a reaction force. In particular, it is the reaction force a surface creates. A surface makes with a body which is in contact with. In contact with it. Okay, so let's take a look at an example. Let's imagine we have a block which is resting on the ground. And let's imagine not only does this block feel its weight here, its mass is 6, so its weight is 6g. Let's imagine we also push down on it with our hand. So we push down on it with our hand with a force of 8 newtons. Now, we know full well that when we push down on this block, unless we're really, really, really strong, the block isn't actually going to move. It's not going to push through the Earth's crust. It's just going to stay there. So that's weird. There's these two downwards forces acting on the block. Surely it should be moving. It should be accelerating. Well, there must be some other force stopping it accelerating. And indeed, the surface of the Earth, because it doesn't want to move, it exerts a opposite force, a reaction force, we'll call it R. Normal just means that it's perpendicular to the surface. Normal is a fancy word for perpendicular. And this R must be such that the block isn't moving. In other words, R must be equal to everything that's pointing downwards. So we have 8 downwards from us pushing it, and we have the weight, which is 6g. So in this situation, we can figure out what the force exerted by the surface of the Earth on this block is. The force is going to be 8 plus 6g. And if you chuck that in a calculator, you'll get 66.86 newtons. Good. Okay, so that's reaction forces. Second. It's gone here. Now, a situation where you'll have to deal with normal reaction forces and where they are maybe the most interesting is in the situation when you're dealing with a block that is resting on a slope. Okay, these are some of the more, at first, I guess, complicated to deal with mechanics or force-based questions. So I already mentioned it, but we're going to be very explicit about here because here it's going to be important and it's easier to get confused. We're going to talk about this normal contact force, the force by the surface on the object. And I said before, normal means perpendicular. In other words, it's always perpendicular to, and this is important, the surface that the object is on. The surface exerts a force, and the force is perpendicular to that surface, not generally to the horizontal, as we will see in this question here. So maybe it's worth just taking a second to ask yourself, where do you think the normal, let me be a bit clearer. We have this block of mass 0.3 kilograms, and it's resting on a slope like a ramp. The ramp is a surface that the block is on, so the ramp exerts a force on the block. So it's worth asking yourself very quickly whether you think, and in fact, I'll ask the chat, is the reaction force, the normal contact force, going to be in this direction? Let's call that option 1. Or is it going to be in 2? In the case where we had a block on the ground, the force went like this. Good, it's situation 2. What's changed here is that we have changed the direction of the surface, and the normal reaction has to be perpendicular to the surface. Good. So the reaction force is in the direction of number 2. So let me draw that in red now to finalize it. Here is our reaction force. It is perpendicular to the surface. Really good. Nice one. Okay, so now we know that, we're in a good position to try and calculate some things about the situation we've drawn on the right-hand side. There's not much unknown in this diagram. Well, there's the reaction force and there's the acceleration of the block. Those are two things we don't know. So we're asked to find both of these, and let's start by finding the reaction force. Okay, so the reaction force. Point 1. How can we figure this out? Well, I'm going to tell you, well, we've been told, in fact, that the box remains in contact with the slope. Now, that means it only moves along the direction of the slope. It could be sliding up. It could be sliding down the slope, but it's never accelerating away from or into the slope. So because of that, we can conclude something. The total force in this direction is 0. Remember, Newton's first law told us that the velocity won't change unless there's a force. If the force is 0, the velocity won't change. The velocity of this block, perpendicular to the slope, is never changing because it can only move along the slope. It essentially doesn't move in the perpendicular direction. So we have an equation. The total force perpendicular to the slope is 0. So let's see what forces there are. Well, away from the slope, there's the reaction force. But what's trying to pull us into the slope in this situation? Well, there's other things, actually. There's this 5 newtons force. So that was so easy to miss, I nearly did miss it. So there's this 5 newtons force here. And this 5 newtons force has a component parallel to the slope, and it has a component perpendicular to the slope. Really hard to draw the perpendicularity there. Okay, so by the Z angle rule for angles, if this is 30 degrees, we know that this is also 30 degrees. That's good. So in fact, this vertical component here is 5 sine 30. So away from the slope, we have r plus 5 sine 30. What about into the slope? Well, we do have a weight. There's a weight pulling our block down here, and this weight is equal to mg, but the mass in this case is 0.3, so it's 0.3 g. Okay. Now, something which is worth just remembering, I won't have time to prove it here, but something it's worth trying to do at home as homework, is that if this angle is 30, or whatever this angle is, will be the same as whatever this angle is. So this angle is also 30. Let me draw that better. Okay, I absolutely didn't draw that better. I made that even messier than before, so let's try again. This is 30. Good. Okay, so given that, and you'll have to assume that for now, and given that this part here is 0.3 g, and we know that this here is 0.3 g times cos of 30. So that's the force in the other direction, and we know these forces have to balance. This is 0.3 g cos 30. Now we wanted to find the reaction force, so let's rearrange. R equals 0.3 G cos 30 minus 5 sine 30. And if you chuck that in a calculator, you'll get 112.779, and that's newtons, which is 13 newtons to two significant figures. Great, so we figured out the reaction force in this really quite initially seemingly complicated scenario where we have an object on a slope, possibly even sliding along the slope. The point is it's in equilibrium in the direction perpendicular to the slope. Okay, but of course it's not in equilibrium parallel to the slope. It's sliding, it could be moving, it could be accelerating. And we're going to figure out that acceleration along the slope now. So now we're going to look at the forces in this direction and find out the acceleration. So let's start with the forces up the slope. Remember that the total force is the mass times acceleration, but also the total force is the force up the slope, which is going to be 6 in this case, minus the force down the slope. So what do we have down the slope? Well, from this 5 Newton force, why did I not include the 6 newtons when calculating R? That's a great question. If you look at the direction in which I was calculating the force, here, I kind of mentioned it here, but maybe I wasn't explicit. I made this comment. The total force in the perpendicular direction is 0. So here I was looking at the forces in that perpendicular direction. And because this 6 Newton force is perpendicular to the direction I was calculating forces in, it doesn't count. So we only care about the forces that are parallel to this direction I care about. That's why, for instance, with the 5 Newton force, I cared about the 5 sine 30 bit, but I ignored the other bit in it. I ignored this 5 cos 30 bit. Why? Because the 5 cos 30 is perpendicular to the direction I cared about. Does that make sense? So it's because I was calculating forces in this direction. And this direction is completely perpendicular to the 6 Newton force. Similarly, it's completely perpendicular to this 5 cos 30 force. And that's why I only included 5 sine 30. Nice. Good, no worries. Okay, so we've got 6 going up the slope, and now I'm ignoring R. So this time, just like you were asking there, why did I ignore 6 newtons? In this case, I'm ignoring R for the same reason. I'm now calculating forces parallel to the slope. R is perpendicular, so it doesn't count. Similarly, 5 sine 30 is perpendicular, so it doesn't count, but the 5 cos 30 does count. So we take away the 5 cos 30. We also have here 0.3 G sine 30. Good. 0.3 G sine 30. So that's going to be our total force, and our total force is hence going to be, if you chuck this in a calculator, 0.198 newtons. Good. And that's mass times acceleration, because that's the total force in this direction. Okay, so now we can calculate the acceleration, again, in this direction. Total acceleration is going to be the total force, 0.198, divided by the mass, and the mass was 0.3 kilograms. So you chuck that in a calculator, you'll get 0.6612, which is, to two significant figures, 0.66 meters per second squared. So that's fantastic. We calculated the acceleration of this object. And that's great, because this is quite a initially seemingly complicated situation where we have a block sliding along a slope. But still, we can calculate its acceleration using Newton's 3 laws. That's all we used. Okay, good. So how's everyone feeling? And does anyone have any questions about what we just went through? Sorry. 2. Okay. Cool. Well, like I said, let me know if you have any questions. While I'm looking out for the questions, in the meantime, I'll get on with going through some exam questions, which may also help. Especially if anyone is confused about the situation with the slope, this is a question which is about practicing our understanding of objects on slopes. So figure 2 here shows a sledge moving down a slope at a constant velocity. You should ask yourself whether you can describe that with a word yet. You should ask yourself using Newton's laws what that tells you about the forces already. Constant velocity. Okay, the angle of the slope is 22 degrees. The three forces acting on the sledge are weight, friction, and the normal reaction force. They're all in the diagram, so I have nothing to draw. That's a great situation to be in. 2a, with reference to an appropriate law of motion, explain why the sledge is moving at a constant velocity. So in other words, what law of motion, and you have two options here really, what law of motion tells us whether something will have a constant velocity or not? It's 2 marks, so we're going to have to state the law of motion and then explain what it has to do with this situation. So since it was slightly low on time, I will just say it. So Newton's first law said an object will stay, we'll forget the rest of it, it will stay at a constant velocity unless acted on by a resultant force. In other words, if there is no resultant force, the velocity is constant. That's what we have here. So the situation must be that the law of motion in place is there is no force. And because there is no total force, there's a constant velocity. So here we can say the resultant force is 0. And so by Newton's first law, what can we say? The sledge must either be at rest or at constant velocity. Indeed, here it is at constant velocity. It is at constant velocity. Good. Okay, so that's a conceptual question, and we're now going to be asked to do some calculations. So maybe I'll need to draw the diagram again here. I think that's a good idea, actually. Yeah, let's do that. So the diagram we had, just for your reference from the previous part, was we had a slope. And we had this angle here was 22 degrees. We had our object on the slope. There was a force F. There was a reaction force R. And there was a weight. Okay. Now, the mass is so much. Calculate the component of the weight parallel to the slope. Now, remember, we have a trick. And the trick says that this angle here is also 22 degrees. It's whatever this one in the corner was. Okay, so using this, and using that this is the weight, you rub this bit out now. Hi, thanks very much. Okay, so using this situation, we have to calculate the component parallel to the slope. Well, parallel to the slope means in this direction. And in this direction, what have we got? We've got this component here. This is W sine 22. So parallel to the slope, the component of the weight is the weight times sine 22. Now, what is the weight? The weight is m times g. And the mass here is 4.5 kilograms. So it's 4.5 times g, which is 9.81, times sine 22. Good, chuck that in a calculator and you'll get 6.537, 16, sorry, 0.537, which is roughly 17 newtons. Good. Okay, now let's go for perpendicular to the slope, and that's just going to be the other component of this weight, which is now W cos 22. So this time we have mg cos 22. Again, the mass is 4.5. Gravitational acceleration is 9.81. And we have cos 22. Chuckle that in a calculator, you'll get 40.930, which is roughly 41 newtons. Good. Finally, and this is a really nice bit of the question, state the values of F and R. Now recall that this object is moving at a constant velocity, which means it's in equilibrium, which means the total force in any direction is 0. So let's start by thinking about the total force in the parallel direction. In the parallel direction, we now know, let's draw the components of the weight properly. We have here the weight, and parallel to the slope, it was 17 newtons. Since the total force is 0, the force up the slope must be the same. So we can conclude that F is 17 newtons. Similarly, in the perpendicular to the slope direction even, we found that the weight in this direction was 41 newtons. Now, since the object is only moving up and down the slope, it's not moving off the slope, it's in equilibrium at a constant velocity, the total force here must be 0. So the force into the slope must be the same as the force away from the slope. In other words, the reaction force, here, must be also 41 newtons, so that everything is balanced, so that we can have that constant velocity. So that brings us to the end of the session, actually. So you should now be able to state and explain Newton's 3 laws. You should be able to calculate resultant forces and determine if a system is in translational equilibrium. And you should be able to solve some problems involving weight and reaction forces. And something that maybe you can't see in here, but is a nice takeaway from today's session, is if you combine all this stuff with your understanding now that you can do Newton's law in any direction, then you can solve problems involving objects sliding down slopes. So hopefully that all made sense. Let me know if you have any questions. And yeah, thanks very much for listening. And thanks for asking any questions you have in the chat as well. So yeah, does anyone have any questions? Okay, so I don't see any questions coming up. And so given that there's no questions, I think we will call it a day there. And thanks very much, everyone, for coming. And I'll see you at the next session, which will be next month. Okay, cheers, everyone, and bye. No worries. Thanks as well. Okay, bye, everyone.